Let's talk about structural induction. Structural induction is a technique for proving properties of syntactic categories defined inductively. So you have some syntactic category defined inductively. So we have the definition of the syntactic category. And by analyzing the structure of this inductive definition, we prove a property of this syntactic category. So an example suffices to show how this technique works. So let's just an example. So previously, we defined this syntactic category NAT for natural numbers, which is defined as either symbol 0 or successor of another natural number n. So this is syntactic category defined inductively, and we'd like to prove some property P holds for every natural number. So here's an example of this property P. So for example, P of n could be n has a successor. Or another example could be P of n is either 0 or successor of another natural number. Or it could be some non-trivial property. So for example, n is a product of prime numbers. And things like this. So we'd like to prove that for every natural number, this property P holds. And the way that this structural induction works is we analyze the structure of this inductive definition. So we first consider the base case and then inductive case. This is called the base case because here we don't see any other non-terminal. But in this case, this inductive case, we see another instance of this non-terminal. So this is the inductive case. So to prove this property, whatever that is, we consider base case first. So first, base case. We want to show the property P holds for this element in the syntactic category NAT. So you have to show P of 0 holds. If this property P was n has a successor, this translates to 0 as a successor. But next, we needed to consider this inductive case. So inductive case. So eventually, in this inductive case, we have to show that P of successor n holds, because this is the element in this in the second branch. So we have to show that P of successor n holds. But now we want to introduce an assumption as an induction hypothesis. Induction hypothesis. So the idea is that we'd like to show that some property P holds for the this natural number successor of n, provided that the same property P holds for something smaller. This n is strictly smaller than the whole natural number here. So we are permitted to make an assumption that the property P holds for this smaller element n. So as induction hypothesis, we assume that P holds for the smaller element, which is n. So this is induction hypothesis. And then the problem reduced to show that this thing holds, this property success n holds by exploiting this induction hypothesis. So if we recall the mathematical induction, essentially in this particular case for natural number n, this structural induction is essentially no different from mathematical induction, where we first consider the first natural number. In mathematics, it's going to be 1, but in our case, it's going to be 0. And then you assume that some property holds for natural number n, and then you show that the same property p holds for n plus 1. So this is the how mathematical induction works. And essentially, we see no difference here. We consider this case as a base case and this inductive case, where we introduce induction hypothesis. So that's the basic idea. Now let's see some slightly complicated example. So previously we defined this syntactic category m-parent for strings of matched parentheses. So S is defined as either epsilon for empty strings or a string of matched parentheses enclosed by this pair of parentheses, or concatenation of two such strings. So this is the inductive definition of m-parent, strings of matched parentheses. And the property that we'd like to show is something like number of left parentheses in S is equal to the number of right parentheses in S. So this is the property that we would like to prove by applying structural induction. So this statement is sort of informal because the number of left parentheses is not defined formally. So let's first introduce two auxiliary functions. Two functions are left and function right. So for visual clarity, let me write this bracket instead of parentheses. So left S is going to be the number of left parentheses in string S. And right S is going to be the number of right parentheses in S. So let's give a definition of this recursive function. So actually it's trivial to define this function if you have completed the programming assignment 1. So in the case of epsilon, it's going to be 0. Let me delete this one. And if the string is this one, then we add 1 to the number of left parentheses in S. And if this is a concatenation of 2, S1 concatenated with S2, then we just add left S1 and left S2. So symmetrically, we can define this function right. Epsilon is 0, and right, right, this one is also 1 plus right S, and right S1, S2 is the sum of the two function calls, left S1 plus left S2. Now we have the formal definition, the syntactic category, and parent is inductive definition, and we have the definition of two auxiliary functions, which are defined recursive. So we have these two recursive functions, left and right. Now, let me translate this informal statement into a more formal statement. So we'd like the proof for every string S in m-parent, we have left s is equal to right s. So this is the theorem that we'd like to prove. So notice that we have this syntactic category defined inductively, and this is basically a property of this syntactic category. So we'd like to prove this theorem by applying structural induction on S. So before we proceed, it helps to visualize the structure of the entire proof. So in our case, there are three cases: this base case and these two inductive cases. So before filling in the details in the proof, let's structure the whole proof. So we are going to have three cases. First case, S is epsilon. And the second case, S is parentheses including something smaller. So let's call it S prime. And finally, we have the second inductive case, which is S is S1 concatenated with S2. So we have these three cases. And again, before filling in the details here, let's first write the conclusion that we want to prove. So for the first case, we have to show that if this is, say, property of S, we have to prove property of epsilon, which expands to left epsilon is equal to right epsilon. And here we have to show that left S, which is parentheses S prime parentheses, is equal to right S, which is S prime parentheses. And finally, in the second inductive case, we want to prove left S, which is S1 concatenated S2 is right S1, S2. So now the remaining job is to fill the gap here, fill the details here. And when you write this proof using induction or similar techniques, you want to write the conclusion on the left side. So whatever comes here should be structured as conclusion on the left side and justification on the right side, not the other way around. This is because if you see the justification first, you might well be puzzled by what this thing really means, what this statement is for. So you want to see the conclusion first and try to make a sense of what this statement means. And then you wanted to see justification. So this is the convention that we write the inductive proofs. So remember, you want to write the conclusion on the left side, and it's a justification on the right side, not the other way. So now let's fill the details in the proof. Right, this is the base case. So there is no induction hypothesis. So we are looking at this base case. So there is no induction hypothesis. So we have to show that left epsilon is equal to right epsilon. But this is almost trivial because left epsilon is, according to this definition, it is 0. And according to this part of the definition, right epsilon is 0. So by transitivity, we have this equality. So the first case is gone. The second case, before you proceed to write the details, you want to state the induction hypothesis first. So in this inductive case, we have one induction hypothesis because we have something smaller here. So we'd like to state that the property P holds for something smaller, which is S prime here. This is going to be by induction hypothesis. So notice that we write the conclusion here on the left side, and it's a justification on the right side. So let me expand this induction hypothesis. Basically, it means that left S prime, the S prime is something smaller here. This one is equal to right S prime. And the justification is induction hypothesis. Now the problem reduced to establish this equality by somehow exploiting this induction hypothesis. And for this particular problem, it's pretty easy. So according to the definition of left, oh, sorry. So according to the definition here, left, this one is 1 plus left s. So according to the definition, this one is actually equal to 1 plus left s prime. Then, by this induction hypothesis, this is equal to 1 plus right s prime. Then, by the definition of the function right, this is equal to the right-hand side of the equality. So by transitivity, we have this equality. So the second case is also finished. And the last case is also similar. You want to start with the induction hypothesis first for the first substring S1. So the induction hypothesis is left S1 is equal to left S2. And there's another induction hypothesis, which is left S2 is equal to, sorry, this is right S1, S2, right S1, and this is right S2. And now we needed to show that this one is equal to this one, and we want to exploit these two equalities. And it's also easy to show because according to the definition, this one is equal to left S1 plus left S2. And now let's apply these two equalities to this expression, which gives right S1. So left S1 is equal to right S1, and left S2 is equal to right S2, which is actually equal to the right-hand side. So we have finished the proof. So the point here is not the details of this proof, but the fact that the whole proof is structured with the first basic case and the two inductive cases. And when you write a proof, you wanted to write conclusion on the left side and justification on the right side. Otherwise, it would be very hard to read your proof because people want to see the conclusion first. And then if they make a sense of the conclusion, they would be interested in why that is the case by seeing this justification. And for each individual case, you want to state the conclusion you want to prove first, and then introduce induction hypothesis whenever possible. And then Structuring your proof this way will help you to feel the details of the proof, and you will not get lost. So in this particular example, it's just a matter of finding this sequence of equalities. That's all.